Okay, why don't we get started? Is this working? Okay, I'm assuming this microphone is working. Okay, just to remind you, after Thanksgiving, you'll have the last quiz of this course. It will cover basically just a short channel MOSFET and fundamentals of bipolar junction transistors, so the material that you just turned in. So the last two homework problem sets and the last, I guess, for four lectures, I guess. Is that right? 2, 3, 4, 5, right. Okay. Also, another announcement is that for the project, for the graduate students, you will need to give an oral presentation. The undergrad students are welcome to attend class during the RRR week to watch the presentations and maybe learn from that. The grad students, you should only come when you're presenting, just to be fair, okay? So Peng is going to pass around a sign-up sheet. So I think there are no more than 8 teams. I know some people might want to work individually, but if there are not enough time slots, we might have to squeeze these down to 15 minutes each. So anyway, so those of you in 2:30, please go ahead and sign up for a time slot to give your project presentations. Okay. Were there any questions left over from the last couple of lectures? No? Okay. I'm sure you guys are ready for pre-Black Friday or something. Okay, so today's lecture, we're going to continue to cover the bipolar junction transistor, but now we have to introduce some basic equations for you to use to be able to calculate the amount of current flowing in a BJT as a function of the applied voltages to the 3 terminals. So as usual, we'll start with an ideal analysis. And next time, we'll talk about non-idealities. Actually, today we'll start to talk about one non-ideality, which is the base width modulation. Okay, so today we're going to just derive some equations for you to use to calculate typical currents flowing in bipolar junction transistors. So we first need to introduce some notation, because now there are 3 doped regions, and there are more than one type of p-type material, or more than one type of n-type material if it's an NPN transistor. So basically, rather than calling it N or P, we would generally denote the parameters in the different regions by the subscript E for emitter, B for base, or C for collector. Okay, so the dopant concentration in the emitter is just going to be N sub E. And if we tell you that's a PNP transistor, then you know the emitter should be P-type. So it's actually acceptor doping concentration in the emitter. Okay, but just for simplicity, we're just going to use the simple single subscript of E rather than NAE. Okay, so N sub E, N sub B, and N sub C will denote the dopant concentrations in the emitter, base, and collector, no matter if the N-type or P-type. You just have to keep track on your own if it's an N-type or a PNP or NPN transistor. And so the minority carrier, let's say diffusion constants and lifetimes, again, we're not going to keep track if they're N for electrons, P for holes. We're going to just keep track of if it's in the quasi-neutral emitter region or quasi-neutral base region or quasi-neutral collector region. And one more notation, it might be a little bit confusing. NE naught refers to the equilibrium concentration of electrons in the emitter. Okay, so the emitter, in this case, is P-type. Then it's the minority carrier concentration, so it's Ni squared over the dopant concentration, N sub E. Because we're assuming the majority carrier concentration is equal to N sub E. Okay, so hopefully you'll get accustomed to this notation, because we need to keep track. So to save a little bit of, because the pen doesn't work so well on my computer, I already wrote some stuff on here, but I'm going to add a little bit more notation. So the overall plan, if we want to derive an equation for current as a function of voltage for these PNP regions, we again have to start with the minority carrier diffusion equations in each of those quasi-neutral regions. Okay? And then we solve the minority carrier diffusion equations, and then so then we can find the excess minority carrier concentrations in the emitter, the base, and the collector. So that's what I'm plotting here. Is just an example of excess minority carrier concentration profile in the emitter, in the base, and in the collector, and it's dependent on the voltage applied across the junction. Okay, so for example, In the quasi-neutral emitter, we have excess electrons. The concentration at the edge of the depletion region is still determined by the voltage that you apply across the base emitter junction. Okay? So that's exponentially dependent on the voltage that you apply across the depletion region. And the excess carrier, minority carrier concentration depends on the, so this over here, this for short is NE0. Okay, so just introducing some shorthand here. Right, it's the concentration of electrons in the emitter at equilibrium. So it's Ni squared over Ne. Okay, so what we're plotting here is the excess minority carrier concentration in the emitter. Under, in this example, it's forward biased, right? Because the excess carrier concentration is kind of elevated at the edge of the depletion region. Same thing here. At the edge of the depletion region, the excess minority carrier concentration is elevated above equilibrium by the same exponential factor, right? This same exponential factor increases the minority carrier concentrations on both sides of the junction at the edge of the depletion region. So here we have forward biased, in this particular example, forward biased emitter junction. And how about the collector junction? In this particular example that I've sketched here, is the collector junction forward biased or reverse biased? Reverse, right? Because it's the carrier concentration on decreasing, well, you can't really tell in the base, towards the depletion region. So basically, minority carriers are being depleted towards the depletion region. They're getting swept across. That only happens under reverse bias. So again, the excess minority carrier concentrations at the edges, the depletion regions are given by the equilibrium value. So this would be P B naught, right? That's the minority carrier concentration of holes in the base, PB naught at equilibrium. It's enhanced by the exponential factor. And here, this is, the notation is NC naught, right? The minority electron concentration at equilibrium in the collector. Okay, so the concentrations at the edges of the depletion region are modified from the equilibrium values by the exponential factor, just like we studied before for p-n junctions. Okay, so we have a forward biased emitter junction, reverse biased collector junction. So what mode of operation are we illustrating here? Forward active. Very good. So it's a forward active mode. And that's the typical mode used for amplification of signals. Okay, so that's the example drawn here. Okay, so we solve the minority carrier diffusion equations in each of the quasi-neutral regions, and then that will give us the excess carrier concentration as a function of distance, which is what I sketched up there. Then we can take the derivative and multiply derivative of these minority carrier profiles, multiply by the diffusion coefficient, multiply by the cross-sectional junction area, and charge. I mean, current is just charge movement with time, so that each electron in a hole is charged with Q. So just like before for a p-n junction diode, we can determine the drift current due to diffusion of minority carriers in each of those quasi-neutral regions. Okay, so let's break it down into little pieces here. So IEN, actually let me change colors here. Okay, so the diffusion right here of electrons. Okay, so let's say the emitter junction is forward biased, so we have excess minority carriers at the edge of the depletion region. Going away from the depletion region, the excess carrier dies, they diffuse, and they recombine in the quasi-neutral regions. So that diffusion current due to electrons in the emitter, which one of these four current components with these equations here, which one of those four is that? It's just one. Which one? Oh, so is that current on the left in the emitter, is that IEN or IEP? IEN, right? Okay, so let's label that. And which direction is it flowing? I mean, the real current. It's actually going to the right, right? Because you have electrons diffusing to the left, so that contributes positive current going to the right. But the gradient is negative, right? Well, sorry, the gradient is positive. Is that right? Yeah, gradient is positive. So anyway, okay, so we'll okay. So in any case, it's contributing current flowing to the right, we know, under forward bias. Okay, let's do the other easy one. The current, diffusion current due to what's going on in the collector. Which current component is that? So this would be IC something, is ICN, right? It says collector current, collector junction current due to electron diffusion. Okay? And again, electrons in this particular case are diffusing to the left, so there's current flowing to the right. Okay. And then due to the gradient right here of holes, you have holes diffusing to the right. So that is ICP. And over here, you have holes diffusing to the right, in the base region at the emitter junction edge, emitter depletion region edge. So that's IEP. Okay, so just qualitatively, that you understand what these subscripts refer to. Okay, so when you bias a p-n junction, you have diffusion of carriers across the junction, both electrons and holes. And so all we're doing here is we're keeping track of the electron diffusion current versus the hole current at each junction. Okay, and the reason, so let's do that. The reason for doing that is because last time we talked about emitter efficiency and we talked about the base transport factor. And each of those together determines the product of those two factors determines the common base DC current gain, and that also that determines the common emitter current gain, right? So remember, let's review. So the emitter efficiency is IEP over all of IE. Okay. So what fraction of the current flowing across the emitter junction is due to carriers going into the base? Okay, that's the emitter efficiency. So it's IEP over the total IE. The base transport factor is how much of the current due to minority carrier injection into the base, how much of that makes it to the collector? That's the transport factor. How many of them are actually transported to the collector? So it's ICP, like how many holes actually are collected by the collector compared to how many holes were injected by the emitter. Okay? So that's why I'm sort of trying to point this out, because later we see these long equations and you might lose track of what we're doing here. Okay? So what we're going to do is solve the minority carrier diffusion equations to find the excess minority carrier profiles as a function of the applied voltage. Then we can derive expressions for the current components, and then we can use those to determine equations for beta, the current gain, and alpha, and so on. Okay, so that's basically what's going to happen in the first part of this lecture. So remember that, the total emitter current, total collector current, each of them has electron and hole diffusion components. Okay, so that's the big picture. This is going to be just pretty much a review of what we did before for the p-n junction. So let's do that. So in the emitter, we have, let's say a depletion region. And let's just say, for example, that we're looking at forward bias. So the excess carrier concentration, we know should ideally, exponentially decay to 0 if the emitter is long. Okay, so this is the excess electron concentration in the emitter. And let's see, so what is the value right here again? It's the equilibrium concentration, so it's NE naught. It's exponential e to the QV EB over KT minus 1, right? So the standard enhancement factor there. Exponential enhancement factor. Oh, okay, I already solved it for you. But okay, so if you go through the process, we write the minority carrier diffusion equation. So this is in steady state, right? So nothing is changing with time. Next week we'll talk about transient response and AC behavior. Okay, so let's say if we apply a bias, we just want to see how much current flows after a long time in steady state. So nothing is changing with time. So remember in the minority carrier diffusion equation, this was a term that was a derivative with respect to time, right? So we set it to 0. And then on the right-hand side, basically this first term represents the change in diffusion current. Okay, if there's any difference if the diffusion current is changing, that means you're losing some carriers due to recombination, right? So this is the change in current, okay, which is mainly diffusion current for minority carrier, and this represents recombination, right? So you have a loss of carriers due to recombination. So we know that if you do have a change in current, diffusion current, then that means you must have some recombination going on. So this is just the minority carrier diffusion equation for the emitter region. The general solution, so if you look at this equation, you can move this term to the left side, right? So basically, the excess carrier concentration, delta n sub E, is equal to, well, it's proportional to its second derivative. Okay, so any function that's proportional to its derivative is an exponential function. That's the definition of an exponential function. And if you take the derivative of an exponential function, you get a derivative again. So any solution to this differential equation must be an exponential kind of function. So it can be exponential to minus x or exponential to positive x. Okay, both of those terms can be differentiated twice, and you can get something proportional to it, to the original expression. So that's why the general solution has two terms. You apply the boundary conditions, so we assume that it goes to 0 far away. The excess minority carrier concentration goes to 0 far away from the depletion region edge. And at the edge of the depletion region, we know the value, right? So you have two boundary conditions at x double prime. So this is x double prime. X double prime is 0. You have a boundary condition, and at x double prime is infinity, far away, you have another solution. So you have this solution, which we know is an exponentially decaying function. Okay, so then now we know delta n as a function of distance. We can take the derivative, and we have an expression for emitter current component due to electron diffusion. Okay, so this is a review of what we did for the p-n junction before. So now let's do the same thing, but for the p side on the collector. Okay, so the p side collector. So again, generically, you have to solve the minority carrier diffusion equation, except now everything is in the collector region. Okay, you have different dopant concentration in the collector region, so therefore you have a different diffusion constant, different equilibrium carrier concentrations. Again, the general solution has two possible terms. You have two boundary conditions. Okay, I'm just going to draw, in this case, it's forward biased in this example. So this is delta n in the collector as a function of, let's say, x prime. All right, and then this value here is nc naught, right? The equilibrium minority carrier concentration enhanced by the exponential factor as usual. Okay, so that's, so you assume, again, that this is a long collector, so it goes to 0. Oops, so it goes to 0, far away from the depletion edge. And so this is the solution, an exponentially decaying function. And you can take the derivative to find ICN. Okay? Pretty straightforward. Now, I just realized I forgot to mention. So last time, when I introduced the basic BJT operating configurations, okay, so I added a few more notes here. So this is the output current. So for a common emitter configuration, amplifier configuration, you plot the current, which is I sub c, as a function of the voltage across the output, which is VEC. So just like for the MOSFET, you draw separate curves for different input voltages, or in other words, different input currents. So I didn't really explicitly ask you why, but So in an active mode of operation, this is where we usually use the transistor as an amplifier. The curves are flat, ideally, okay, flat. And the emitter junction is forward biased, so you have significant base current. And the collector junction is reverse biased. And as you change the output voltage, you're basically changing the reverse bias on the collector junction. And that shouldn't have too much effect on your collector current. Okay, so just the terminology might be confusing, but basically if you go to very low VEC, what that means is that if VEC is actually less than the forward bias on your emitter, okay, so that's right here. If VEC is less than the forward bias on your emitter, then that means VBC is less than 0, is negative. In other words, the collector junction is forward biased. Okay, so if you go to very low VEC, below the forward bias on the emitter junction, then that means what you're doing is you're forcing the base collector junction to be forward biased. Now, when the base collector junction is forward biased, you're injecting carriers like for a PNP transistor, you're injecting holes into the base from the collector, right? So in this saturation region, the reason why they call it saturation is because the base is becoming saturated with excess minority carriers. That's why they call it saturation. Okay, so it's a different way of using the word saturation than for the MOSFET, right? For the MOSFET, they call it the saturation region, kind of where the curves are flat because the current saturates. But in a BJT, the saturation region is actually this region to the left, okay, where the current actually, IC actually becomes less than beta IB because you're injecting holes like in the wrong direction. And so holes are, minority carriers are piling up or saturating the base, the quasi-neutral base. Okay? All right, so that's a difference with BJT terminology. Okay, so in this particular example that I sketched here is just deriving the equation for positive forward bias on the collector junction. But of course, this equation still holds even if the collector to base bias is reverse bias, right? Because if VCB is negative, then basically the current will just be a small, All right, any questions on emitter or collector region? Okay, so here comes the the hard part is the base, okay? So let's see what's going on in the base. Let me, okay, I'm going to get ready to change my pen colors. Okay, so let me just sketch the, let's see, the base region here. So let's say there's a depletion region here, the emitter depletion region, and we have a collector depletion region on the right. Okay, so we're just looking at the N-type base in the middle. Okay, so you still have to solve the same minority carrier diffusion equation for the base region. Again, now the minority carriers are holes, and you have to use the correct diffusion coefficient for holes in the base, depending on the dopant concentration in the base. Oh, this is, sorry, that's a typo, right? This should be a P. Okay. All right, so it's, wait. This is N-type, right? Okay, that's right. All right, so this is N-type. N-type, yeah, did I do this wrong? Yeah, that should be P sub B, right? Okay, I'm just getting myself confused. So we're keeping track of excess minority carriers in the base, so it has to be holes, so P sub B. Okay, so we write the same minority carrier diffusion equation, except we have to have different diffusion constant and minority carrier lifetime appropriate for the base. The general solution is still the same, right? It's just some e to the minus x something and e to the positive x something. There's two possible solutions. Each of them can satisfy that differential equation. Now the boundary conditions, two boundary conditions. Okay, so what is the excess carrier concentration at the emitter depletion region edge? not, right? The equilibrium concentration level enhanced by some exponential factor. So let's see, this is BEB, right? We know that excess carrier concentration has to be, this is the law of the junction, elevated there. Let's draw a forward bias collector as well. Let me just draw this. Color. Okay, so the collector junction, what would be the carrier concentration there? Still the minority carrier concentration at equilibrium, but now it's enhanced by a different exponential factor, right? Because it's VCB that's applied to that junction. Okay, does that make sense? So qualitatively, so now you have two boundary conditions, and you basically you have two equations. So right, you have two equations, two boundary conditions, so you can solve. Okay, so if you go through the algebra, you'll find that the solution does have two terms. Okay, one that's exponentially dependent on the base emitter bias, the emitter junction bias, and then the other one that depends on the collector junction bias. So let me just sketch here. So let's say both junctions are slightly forward biased. So one, well, if this is a long base region, then you expect the carriers to injected from the collector to the excess carrier concentration to die out to 0 over distance. And for the carriers injected from the base, from the emitter, you also expect those to die out with the same exact diffusion length, right? So if this thing dies out, like if the diffusion length is roughly, this distance, then this thing should die out within that distance as well. Okay. So both junctions in this case are injecting holes into the base, and you just basically end up with something that is essentially the sum of these two. Okay, so in this particular case, I think the current should look sort of like this. Sorry, it's going to be, you add them, okay? And the excess carrier concentrations, you add them together. Okay, I'll clean that up later. Okay, so this is kind of like a little bit messy. This exponential of some argument minus the exponential of minus that same argument. So we can take advantage of the fact that hyperbolic sign is sort of a shorthand for writing, exponential of something minus exponential of minus the same argument. So this is in the middle here. That's exactly the same expression for the excess hole concentration in the base as on the previous slide. And all we're doing is we're rewriting it in terms of hyperbolic signs. Okay, that's it. So this should look a little bit similar to, let me just show you, lecture 11, where we talked about sort of short base diode, right? So hopefully this kind of looks similar. It's exactly what we did before. All right. Okay, so let's go back. So now we have this expression for excess carrier concentration in the base. Now we have to take the derivative to find the current, right? The current at the edge of the emitter junction, that's IEP, and the current at the edge of the collector junction, which is ICP. Okay? So the derivative of the hyperbolic sign is the hyperbolic cosine of the same argument. And if you work through the math, it comes out to these messy, very messy terms, messy looking terms here. Okay? But the key is that we've derived now expressions for IE, the whole diffusion current entering into the base, and this is the whole diffusion current exiting the base. Okay? So we take the ratio of those, and that gives us transport factor, base transport factor. Okay, so now, so basically, well, all I did was on the top here is take the equations we derived on the previous 3 slides where we summarized IE and IUP ICP and ICN, just put them all in the same spot. Then we can add the IE, the emitter current, diffusion current components together to get the total expression for I sub E, the emitter current. Same thing for I sub C, add the N and P components. So you get these nice long looking equations for the current. Okay, but we know in reality, to have high gain, we talked about last time, the base should be narrow. Okay, so the base really should be much shorter. This quasi-neutral base region should be much shorter than the minority carrier diffusion length in the base. That way, you'll have negligible recombination of holes when they diffuse to the base, and they'll all make it to the collector to be collected. So you have close to 100% transport factor. Okay, so the nice thing is that we know in reality, okay, we usually have a short base. So a short base means that this W over LB, so forgot to remind you, W is the width of the quasi-neutral base region. Okay? So if the width of the quasi-neutral base region is very small compared to the diffusion length, right, this minority carrier diffusion length, then this argument, for the hyperbolic cosine and hyperbolic sine is really small. And the nice thing is that, well, if you want to keep track really closely, okay, you can keep track of this little term here. But hyperbolic cosine essentially goes to 1, approximately 1, if that argument is really small. And then hyperbolic sine actually can be replaced by the argument if it's very, very small. Okay, so just like before for the short base diode, you end up with a straight line. Okay, so now in this case we have a reverse biased collector, and we have a forward biased emitter. But the key is that the slope, right, the slope of the excess carrier concentration is constant. It doesn't change. It's not getting steeper. It's not getting steeper as you go with distance. Because you're not losing carriers to recombination. So any carrier that is injected into the base at the emitter side is going to be collected into the collector depletion region. Okay, so slope is the same at the edge of the emitter as at the edge of the collector. Okay, so if you remember, so gamma, this is defined to be ICP over IEP. Okay, so if you take into account that the base is very narrow, and then you can get the, gamma is IEP over IEP plus IEN, right? That's the emitter efficiency. The transport factor is ICP over IEP, right? Okay, so if you actually take all those expressions on the previous slides, assuming that the base is very narrow, you can actually arrive at these relatively compact formulas for the emitter injection efficiency, the base transport factor, and therefore current gain. Okay, so ordinarily, let's see, did I say that somewhere? Maybe not. Okay, so ordinarily, W over LB is very small, and this ratio here is actually, let's see. Well, this one, okay, usually this in a denominator, the second term, you can design it to be small, right? So also remember the typical minority carrier diffusion lengths are more than 10 microns. In a modern BJT, the width of the quasi-neutral region is on the order of 1/10 of a micron. So we're talking about this factor being like 10,000, 1 over 10,000. So it's pretty small. It couldn't be easily an order of magnitude or more smaller than this other term in the denominator. So let's just write this like this, NIB squared write the simple expression for WB, sorry. Okay. I think that works. Okay, so this is an approximate expression for the current gain. Okay. So there's something, oh yeah, so in the box, right. So ordinarily in a modern BJT, also the emitter's short. Okay, so rather than having L sub E in these equations, including here, you would just have the width, the width of the quasi-neutral emitter in the expression. Okay, so just in the red font there, if we have a short emitter, then just instead of the diffusion length, we just replace it with the quasi-neutral emitter length. Okay, so last time, remember I mentioned, we usually would like to have high gain, and so to do that, we want to make the emitter doped more heavily than the base. Right? So this is consistent with that. And also, we would like to have the base width be relatively short. But remember, if the emitter is doped much more heavily, like degenerately, then the emitter can have some band gap narrowing. So Ni squared can actually go up. And that's counterproductive for enhancing the current gain. Okay, any questions about just qualitatively how we derive those equations for the current as a function of the applied biases? And then the BJT performance parameters. Okay, we'll come back to that in a little while. All right, so now let's talk about a model. So basically, the Ebers-Moll model is what we call a large signal model. So it's not used to model small changes in current as a function of small changes in voltage. But it is used simply to help you determine, okay, how does the current in the transistor terminal change with an applied, with a chain, okay, how does it depend on the applied voltage? Okay, so basically the Ebers-Moll model tells you what IC is and what IB is, and therefore if you know IC and IB, you know IE. Okay, so it gives you equations for IC and IB as a function of V, B, VC, and VE. Right? So if you know the voltages applied to the emitter junction and the voltages applied to the collector junction, you should be able to determine what IC and IB are, given that you know the dopant concentrations and the widths of all the regions of the BJT. Okay? So yeah, bottom line is used to calculate at least two of the currents, and if you have two of the currents, you have the third current from Kirchhoff's current law. And you just need that, to be able to calculate the current, you just need the voltages applied. Okay, so these are the same equations, the full equations from an earlier slide, not taking into account that the base is usually much narrower than the diffusion, minority carrier diffusion length. Okay, but basically what we want to show here is that you have two terms, right? So you have one term for the emitter current that's due to base emitter bias. Right? So if you put a bias on the base emitter junction, you'll cause current to flow across that junction. Okay, let's look at the collector current. It might be easier. Okay, so on the collector current, collector junction, you have some current that depends on the base emitter voltage. Okay, so the collector current is dependent on the base emitter voltage because the base emitter voltage determines how many holes are injected in the base, and those holes are mostly collected by the collector. Right? So basically, hopefully that makes sense. That's the purpose of the BJT, having two PN junctions close together. The current flowing in the output terminal is affected by the voltage applied at the input terminal exponentially. Okay, but if you apply a forward bias to the collector junction, you can also cause current to flow across into or out of the collector. Okay, so that's what the second term is about. Okay, so if you look at the equation for the collector, basically this term here, oops, this term, this big term here, this is actually equivalent to the normal saturation current for a diode for the base collector junction. If you look at it, okay. So this is the normal diode saturation current for the collector junction. And then what you have to add to it is this extra current that can flow due to a minority carriers injected close to that collector junction. Okay? But the current that is injected by the emitter, only part of it makes it to the collector, right? Some of it might be lost to recombination in the base. So that's why the collector current actually, oops, where is it? Okay. So if you have no base collector voltage applied, okay? In other words, if this VCB is 0, then basically you have no current flowing across the across the diode, right? The base collector diode, okay? So if VCB is 0, there really should be no base collector junction diode current. But you do have current due to current flowing, you have current collected by the collector due to the emitter junction, okay? So that's this term here, right? So this term is dependent on the base emitter voltage. But only a fraction of the base emitter PN junction current actually makes it to the collector, right? Only a fraction gets collected. So that's why you have this alpha F. So this is like the alpha forward common base gain. But anyway, it's just some alpha is just some factor less than 1, right? So some fraction of this normal collector base PN junction current, normal emitter base PN junction current actually makes it to the collector. Okay. Now, if there's no current flowing in the base, okay, the emitter current is just going to be the normal PN junction emitter current. Right, so let's see. So if you look at this equation here for IE, it's basically a PN junction equation, right? Except that IF naught is now the saturation diode current for the base emitter PN junction. Okay. So let's see. Let me just write that down. IF naught is equal to QA. That's going to be a little long here, but and this is only assuming a non-short emitter. I'm going to put those arguments there, but you know what's in them, right? Okay, so if you look at this equation for the saturation, the normal diode saturation current for the base emitter junction, it has one term that corresponds to electron diffusion and another term corresponding to hole diffusion. But the hole diffusion is happening in a short base, and that's why you have this hyperbolic sign and cosine there. Okay, so the point here is that if you have zero bias on the collector junction, then ideally that bias is not contributing any current. The only current that flows is the normal current that flows in this PN, the base emitter PN junction. And part of that current can be collected by the collector. And whatever is not collected by the collector shows up as base current. Okay, so that's why you have this 1 minus alpha, right? So we have IE equals IB plus IC, right? So emitter current that flows, part of it goes to the collector, part of it goes to the base. So you can do the same thing, except now for the collector junction. So now let's set the base emitter voltage to 0. So no current should be flowing normally in the base emitter PN junction. And the only current flowing in this BJT is due to the collector junction bias. Okay, so then now again, so the collector current just looks like a normal diode current equation, right? Except now you have a slightly different diode saturation current expression for the base collector junction because you have different collector doping compared to the emitter doping. Okay, so this is the normal equation for a short base collector junction. Now part of that, again, if you have a forward bias collector, part of the holes that get injected in the base can actually diffuse and get collected by the emitter junction. So the emitter actually can have some current flowing even though you don't apply a bias to the emitter junction, right? It's just collecting, because you have a depletion region that will collect minority carriers. And so a fraction, again, a fraction of the minority carriers injected by the collector junction can be collected by the emitter to show up as emitter current. And the holes going out to the left are negative current, so that's why you have this minus sign here. And IC and IB have to sum up to IE, so that's how you get. So whatever current is not collected by the emitter shows up at the base. Okay? So the Ebers-Moll model basically adds these two cases together. So we came up with equations separately for IC, IE, IB if one junction is zero biased. But in reality, in general, either junction can be forward biased or reverse biased. Okay, so basically, the Ebers, in the general case, you have to keep both terms. Okay, so let me go back here. So this alpha R times IR is actually equal to alpha F IF. If you look at these equations, let me highlight it. Let's see, it's this one, this term here. It's actually, yeah. So these two terms are the same. So that's basically this reciprocity relationship. Okay, so let's finish this up. Okay, so this is the Ebers-Moll model right here. Okay, so you have a PNP. Let's write this down. So this is a PNP transistor, and as you expect, it's two diodes, right? On the left, you have a diode pointing to the right. So you have P on one side, and on the right, you have a PN junction diode, but it's pointing in the opposite direction. So it's basically these two diodes are sort of back to back or face to face, whatever you want to say, right? So that's PNP. So you can model the current flowing into the emitter, the base, and the collector terminals as two diodes that are facing each other like this, okay? But because it's a BJT, because the base region is so short, you actually can have current due to one diode showing up at the other diode. Right? So it's a fraction, some fraction of the current, let's say, so some fraction of the current due to forward bias on the emitter diode will show up in the collector. And that's the alpha F factor. And if you bias it, if you forward bias the collector junction, some fraction of that forward bias current in the collector junction will show up as emitter current. And that's it. Okay, so that's the Ebers-Moll model. So now if I give you like VBE or VEB and VBC, you should be able to calculate IE and IC and IB, assuming that I give you, alpha F and alpha R and IR and IF. Okay? So you'll have a short homework problem on that. Okay, any questions about the Ebers-Moll model? It's just simply used to calculate currents for a given bias voltage. Okay? Okay, so I think the final topic is base width modulation for today. Okay, so as I mentioned before, last time I sort of sketched out the output characteristics. The textbook curves are ideal in that in the active mode of operation, ideally, as you change the output voltage, the output current doesn't change. But in reality, we know that if we increase the reverse bias on the base collector junction, the width of the depletion region increases. Right? So the width, I'm going to exaggerate. The width of this depletion region, okay, it's much wider on this side. I'm going to exaggerate. Okay, so the width of the depletion region will get wider as you increase the reverse bias on the collector junction. Okay, so as I indicated here, if you're going to the right on this IV plot, larger VEC means larger VBC, which means larger reverse bias on the PN junction, the collector PN junction. So if you're changing the width of the depletion region, then you're causing the excess minority carrier concentration to go to zero sooner, right? Across a shorter distance. So the slope, the gradient of the excess carrier concentration is steeper. So the diffusion current will get higher. Right? So as you increase the reverse bias on the collector junction, you're going to decrease the width of the quasi-neutral base region and therefore increase the diffusion current being collected by the collector junction. Okay, so that's a phenomenon called base width modulation. And if you want to rely on equations, beta, the current gain, which determines IC as a function for a fixed. So remember, each curve is for a fixed value of IB. So this base width modulation effect will cause, for a fixed IB, IC will increase because beta increases, right? So basically, beta is increasing because, well, if you look at the equation, there's a W on the bottom. Okay, but qualitatively, you should be able to explain that, the slope, the minority carrier, the excess minority carrier diffusion, the excess minority carrier profile gets steeper. Okay. Right. Any questions qualitatively about the base width modulation effect? All right. So the question, okay, so it's not actually desirable. For a small signal, if you want to use a transistor as an amplifier, it actually reduces the small signal gain. So we actually like to keep the curve flat. So next week we'll talk about the small signal model again to review why slope is not desirable. Okay, so how do we minimize the base width modulation? Well, 3 ways. We can increase the width of the base. So if, so this increase in depletion width, okay, if the width of the base is really large compared to the width of the depletion region, that's not going to make too much difference. Okay, so that's one way we can reduce the base width modulation effect. But what's the downside? What's the trade-off if we do that? If we increase the base width, yes, we can make the curves flatter. But what is the trade-off? More recombination, that's right. So more chance for carriers to recombine before they get collected by the collector. So in terms of transistor performance parameters, what does that mean? Less gain, that's right. So specifically, so gain is going to be is a function of, there's the emitter ejection efficiency and the base transfer factor, right? Which one of these is actually most affected when you increase the base width? Transfer factor, right. So transfer factor goes down. Okay, but so that means that gain goes down. This kind of explanation is kind of all you need, like if I give you a quiz, okay, or a final exam. All right, that's sufficient for justifying, qualitatively changes that we make to the transistor design. Okay, another way to reduce base width modulation is to make not the base width wide compared to the compared to the depletion region, but to make the depletion region narrow. Right? So we don't have to make the base so narrow. Okay, so if we make the depletion region narrow, we can minimize the base width modulation effect. Okay, so we can do that by increasing the base dopant concentration. So remember, for PN junctions, the more heavily doped a PN side of the PN junction is, the smaller the depletion width on that side. So we can increase the base dopant concentration. Okay, what's the trade-off here? There's always a trade-off. Beta, okay, yes, you're right, beta goes down, but now why? Which one of these factors? Gamma, right? So the emitter, so the gamma goes down. So if you dope the base more heavily, then you have more carriers injected from the base into the emitter when you forward bias the emitter junction. So gamma, the emitter efficiency goes down, and that causes current gain to go down. Okay? Great. Okay, so another way is to decrease the collector dopant concentration N sub C. That helps because, well, if the collector is much more lightly doped than the base, then all of the depletion region pretty much is in the collector, not in the base. So the base will be hardly depleted. Okay? Any downside there? reverse something. Let's see. If you more lightly dope, that's true. That's a good point. Okay, so let's see what Ali is saying here. If we look at the current flowing in a collector, yeah. So what you're saying is that this normal, reverse bias, this leakage, whatever, this minority carrier collection term here, right? This little current component number 3 actually becomes more significant. That's true. Let me think. But in the collector, let's see. Okay, so what you're saying is then, okay, if we dope the collector more lightly, that doesn't that. Okay. So these terms. Okay, so each of these small arrows 3, they increase in magnitude. That's true because the built-in potential barrier is smaller. Is that good or bad? I don't know. Not so bad, I guess. Not as bad as the other trade-offs that we're talking about here. But you're right, so that there is always some impact. Okay, so it turns out that out of these 3 approaches, this is probably the best one. But yeah, what happens is the resistivity of the collector region is increased. So basically the series resistance increases, so that actually can start to cause some issues. But that's why, okay, so of the above, the most acceptable action is 3. Okay, but that's the reason why in a, I think we'll cover it next time, in a modern BJT, we actually have, okay, we have N plus, contacts here. We actually have heavily doped regions down here, the so-called sub-collector, just basically to reduce the series resistance effect. So you have the emitter, the base, the N-type base, and the P-type collector in this case. Okay, so people make structures like this just to mitigate the series resistance problem. Okay, very good. Okay, so from a circuit designer's standpoint, they care about the slope, okay, because that determines the small signal voltage gain. And so one parameter that people like to report, let's say in papers or when you buy a transistor with some specifications, they give you the current gain and they give you also the early voltage, V sub A. So let's define the early voltage here. It's actually defined already, right here. It's defined to be, well, it's hard to explain, but it's shown on this slide, right? If you take the slope of the output characteristic and you extrapolate it down to 0 current, ideally, all of these curves should intersect at a certain voltage, and the early voltage, I think, usually is considered positive. So the larger the early voltage, the flatter these IV curves are in the active mode, and the better it is. So the larger the early voltage, the better for high current gain, high amplifier gain. So we'll talk about amplifier gain next time. Okay, so bottom line is we want a small slope, which is DIC dV EC. Okay, or that we want a large inverse slope. So if we take the inverse of the slope, that's defined to be the output resistance. Okay, so we'll cover that again on the small signal model. Okay, so finally for today, let's derive a simple formula for the early voltage, just to give you some insight into how you would design a BJT to have a large early voltage. So early voltage ideally should be more than many volts. I mean, should be many volts, like 5, 10 volts. The higher, the better. But in a modern BJT, it might be several volts. Okay. Okay. So So the goal here in the next 2 slides is simply to derive a simple equation that shows you how you can change like the doping or the width of the, actually it's really the base, to get a large early voltage. So in the past we've had, as a design project, designing a BJT to get certain gain requirements and so on. And the most critical parameters actually are the width of the quasi-neutral base and the doping in the quasi-neutral base. So just like for your MOSFET, you might be finding out if you tried it that if you change the gate length, you can change things quite a bit, the threshold voltage and therefore on-off current ratio. But for the MOSFET, again, the middle region is the critical region. The doping in the channel and the channel length will determine your transistor performance. Same thing for a BJT is the base region that's critical. Okay? So let's derive some simple equation here. So we do this by breaking this down. Let's see, how do we do this? Okay, so let's just go down here. The output conductance, we would like that to be, okay, remind me, do we want that to be large or small, the output conductance? Small, that's right, because we want the curve to be flat. We don't want the current to change much as we change the output voltage. Okay? Okay, from the previous slide, we can come back to this on the next slide, but the early voltage, the reason why it's determined like this is because we're assuming that this, so I sort of added this last time, but where these curves start to fall down, that's when when the IC starts to fall down, when you start to forward bias the collector junction, right? If you forward bias the collector junction, you're injecting holes like in the opposite direction, counterproductively. So basically, you're forward biasing the collector junction when you are starting to see this current fall down in the saturation regime. So usually that means the collector junction is counteracting the built-in the emitter junction forward bias. So bottom line is the voltage here, the VEC, is rather small, okay, in the saturation regime. Okay, so we're sort of approximating that it's close to 0, and that's why this simple equation for the early voltage actually works pretty well. Okay, anyway, so let's see. So the key thing here is to remind you, each of these curves is for a fixed IB and hence fixed V. So if you take a derivative with respect to VEC, right, you're just taking a slope with respect to VEC, it's the same as taking it with respect to, so VEC equals V plus VBC. So if you take a derivative of this, this thing's going to go to 0 because it's not changing. And so basically, a derivative of VEC is the same as, a change in VEC is the same as a change in VBC. Okay, so that's why we care about the derivative with respect to a change in VBC. Okay, so that's just the change in the reverse bias voltage on the collector junction. Okay, so now we can, this is the chain rule. Basically, the change in current with the change of the reverse bias voltage on the collector, you can break it down into two parts. Change in current as a function, as a result of the change in the depletion width times the change in depletion width due to a change in the collector junction reverse bias. Okay, so we'll just break it up into two factors like this. Now the change in the width of the depletion region is going to be equal to but opposite sign to a change in the width of the depletion, sorry, did I say? Okay, the change in the width of the quasi-neutral base is going to be equal in magnitude to change in the width of the depletion region in the base region, except it's the opposite sign. Okay, so we're introducing a new little term here, the depletion region width in the base at the collector junction, X sub NC. Okay, so basically now instead of this factor here, taking into account the change in the depletion, the base width, we're just keeping track of the minus change, the opposite direction change in the depletion width. Okay, so the wider the depletion region, the smaller the base region. Okay. So this is the same. Okay, this is the same equation as we wrote on the earlier slide, but now we're assuming this is a narrow base. Okay, so it's a simpler equation, and I think we're assuming that VCB well, we're assuming that this term is negligible, right? That the current contributed by that reverse biased collector junction is negligible. Most of the current that is collected by the collector or flows through the collector is just due to exponentially large current that's injected by the emitter junction. Okay, so now we have a relatively simple equation for the collector current. Let's differentiate that and see how sensitive it is to the width of the quasi-neutral base region. And if you take the derivative, you basically get the current back, but divided by W. Okay, so here's the first factor. Okay, let's see. Does this make sense? The change in current for a given change in base width. Okay, so if base width increases, do you expect the collector current to go up or down? The base width gets wider. Current goes down. Right, so the minus sign makes sense. Okay, and let's see. Well, if you're operating at a higher current level to begin with, then you should be more sensitive to changes in the base width. Okay, so qualitatively that kind of looks to make sense. Okay, now to get this an expression for the second factor in the output conductance, that's here. It turns out to be dependent on the junction capacitance. Okay, okay, so let's explain why. So the charge on either side of the depletion region, is just going to be equal to the dopant charge concentration, and the dopant, the charge, what is it called? The charge density, okay, QNB, and the width of the depletion region in the base. Okay, so this is just simply as implied Q depletion on the N side of the collector junction. If you take the derivative of that with respect to the reverse bias voltage on the base collector junction, you can get QNB, assuming NB is uniform, we get this expression here. So this is the factor that we're looking for. Okay, so now we can write this factor as a function of the collector junction capacitance, the depletion capacitance, and the base doping. So if you take this times this, you'll end up with okay, so that's G naught. But now the early voltage is IC over G naught, so you just plug that all in, and you end up with a simple expression that should provide some insight, ideally, into how to design a bipolar junction transistor with relatively large early voltage, okay? Relatively flat active output characteristic. Basically, NB times W, okay? So what does that mean? That means if you want a large early voltage, you should dope the base kind of heavily, and the base should not be too narrow. But then, as we mentioned before, there's some trade-offs, right? But in any case, that's the key thing to remember for early voltage. Okay. Any questions qualitatively? Yes, Ali? Oh, is there any reason why we did it this way with the X and C? Oh, why do we keep CJC? Okay, so the question is, why do we want to write it in terms of CJC? Well, also it tells us, okay, if the junction capacitance is too high, then that's actually, in other words, if the collector is doped too heavily, then the junction capacitance will be higher, and that's not good either. It's counterproductive for VA. So I guess we keep it like this so that we can capture all of the basic, qualitatively, all the design considerations to get large early voltage, to get high small signal gain, because this has implications for junction collector doping as well as base doping and base width. Yeah, I mean, but this is only for early voltage, right? There's trade-offs, right? If you have heavy base doping, then you have lower emitter efficiency, and then if you have large W, then you have lower transport factor. So that, like any design project, you have a trade-off in the design factor. So the key is for early voltage, if you're if you were working on a BJT design project, then you would know that, okay, these are the key things, the key knobs to tune to try to improve the early voltage. Because yeah, when we used to give a BJT design project, we actually specified the early voltage has to be greater than something, right? So these are the factors to tune for the early voltage. But then you know but then you also know the dependence of these performance and the current gain, which is another performance requirement on various factors. So these are just ways for you to see, okay, which design parameters do you adjust to try to meet all your performance specs. There's multiple constraints, right? Okay, that's pretty much it. Okay, so next time we'll start to cover non-ideal effects, and we'll end with time varying and transient performance of BJTs. Okay, all right. Have a happy Thanksgiving if I don't see you at the social hour next.